rewriting systems. A reduction strategy or rewriting strategy is a relation specifying a rewrite for each object or term compatible with a given reduction relation. Some authors use the term to refer to an evaluation strategy. So, let's imagine some rewriting system, and they have some objects in this system, or terms, or points in a graph, and they have some reduction rule. Actually, this is the arrows in this graph. And we can reduce our terms or points in different ways. In a most common scenario, we, for example, may have one point and another point, and there exists more than one arrow which come to this point. Or maybe there exist arrows which come to other points. And what reduction arrow we should use? There exist many of them. And actually, if they have some rules which define to us how to choose these arrows, we have these rules represent the reduction strategy. Let's define the reduction strategy more formally. So we can say that if they have some abstract writing system. Actually, the abstract writing system is a pair of two objects. The first object is a set of our terms, and the second object is this arrow. Actually, this is the reduction relation. Now we can define our reduction strategy. We can represent this notation as arrow S, arrow strategy. And actually we can define it as a binary relation on A, which can be notated as, so actually this is the subset of our arrow plus relation. The arrow plus is the transitive closure of arrow, but it is not reflexive closure, because at every reduction we want to have some changes. We don't want to stay at the same point. Okay. Actually, this is the arrow reduction is homogeneous reduction, because we have the set of A's, and they are always in this set. They do the transformations inside this set. We can classify our reduction strategies into one-step reduction strategy and many-step reduction strategy. So here we can say that one-step reduction strategy is just some subset of the arrow, our initial arrow or reduction relation. So this means that in every pair of this relation they do only one reduction step, as small step as possible. And otherwise it is many-step strategy. What is otherwise? Otherwise they have this our arrow star as subset of arrow plus. So we add the transitive closure. We have now transitivity. And this means that we can do not these small steps, we can do the big steps. Also, we can classify our strategies into the deterministic strategies and non-deterministic strategies. What are the deterministic strategies? This is the strategies where we can do only, we can choose only one possible step of reduction. So we have no ambiguity at each step to choose. And otherwise, the non-deterministic strategy, we have many steps, and we must we can go in parallel, I think, and have many different branches of the reductions. So, and we can see that it is a partial function, because at some point we need to stop, yes. And more formally, a deterministic strategy is a strategy for each A that belong to A. They say where is at most 1B, such that A is reducing to B. Otherwise, it is a non-deterministic strategy.